Okay, U4L2. So hopefully, again, you're starting to kind of get an idea of what we talk about when we talk about energy. Right now, we are going to make 2 note cards. So if you can grab 2 note cards, I have them at the front of the room. We are making one for kinetic energy. Now, there's a reason why I'm having you guys write translational kinetic energy. Translational kinetic energy just means moving one thing and keeping the same orientation. Later, we're going to learn about rotational kinetic energy when things rotate. So these are different formulas. So we're going to call this translational kinetic energy. We're going to call it that for the note card, but I won't ever actually in this unit refer to it as translational because it's not going to matter until we learn about rotational. So these are the 2 main types of energy that we're talking about: kinetic and gravitational potential energy. Very often I'm just going to say potential energy, but it really is gravitational. The potential to have energy due to gravity. So go ahead and pause I'm going to have you pause the video here. You're going to copy this note card and then click continue when you're ready, and then you can scroll down and copy the next one. Okay, so here is our translational kinetic energy. I'm just talking about this really quickly though. The units for this are J, which did I did not. I need to be careful about this. Got to fix these notes. J is joules. You can add that to your note card. So you ever heard of this concept of a joule? A joule is a unit of energy, or actually Newton meters as well. A joule equals a Newton meter in the same way that a Newton actually equals a kilogram times meters per second squared. We like to give some fancier units names, but a joule is equal to a Newton meter, and it has to do with the formula here, that it's mass times speed squared. Actually, this is not velocity, because kinetic energy is actually a scalar. Energy doesn't have direction. If I run forwards or backwards, as long as I'm going the same speed, I have the same amount of energy. And hopefully that's something you can understand. It doesn't have a direction, so it is not a vector. Kinetic energy is a scalar, not a vector. Okay. And scrolling down here is the gravitational potential energy. Now again, you're going to copy 2 formulas down here, but we're really going to focus more on one of them for right now. This is the main one: mass times gravity times the height. When you're on Earth, right, gravity is 10. This formula is talking about the potential between any 2 objects that can create a gravity. So take a second, copy this down. And then, so one thing to note here is that UG is the symbol. It's not actually P for potential energy. P is actually a different variable for something else. So they use U for potential energy. I don't know why. It is what it is. Let's go ahead and keep going here. So we talked about in the last lesson that an object by itself can have kinetic energy when it is in motion. I have my cup here and I'm moving it. This object of the cup currently has energy, right? But as I'm holding it, the cup does not have kinetic energy. Yeah, it does have the potential to have kinetic energy if I were to drop it, right? Because of the Earth, right? Because of gravity. So if we include gravity in the system, Earth in the system, then yes, I can say this cup does have potential energy because the Earth gives it that potential. So really quickly here, we're just going to practice with the formula. So it says an object of mass 3 kilograms is being held at a height of 15 meters. What is the potential energy of the object? So really quickly, look back to your note card. We're on Earth. Our basic formula for potential energy is, copy it down, M mass times gravity, 10, times the height, right? So this is just very basic. Ooh, God, pause. I'm going to erase this. Okay, backtracking here. So practicing with the formulas and practicing understanding the concept of an object versus a system how the potential energy works for that. So it says, what is the potential energy of the object? So this is not a trick question. These are unfortunately questions that will actually be asked on the AP test. The object by itself, yeah, is just being held. Does it currently have any by itself potential energy? No. If I define my system to be a singular object, I cannot say that object has any potential energy because if just the cup is inside the system, there's nothing inside the system that can give it energy. But if I define my system to be the object Earth, right? Well, now the Earth is inside the system, and this cup does have potential, or I should say the system as a whole does have potential to convert from one type of energy to the next. So once again, we have the formula here. This is the basic formula. Mass times gravity times height. Excuse my terrible handwriting. So gravity is just 10, right? So the mass is 3. Gravity is 10, and my height is 15. So what is this? 30 times 150, sorry, 15. 450. And again, look back to your note cards. What is the units for energy? It is joules. I'm going to keep emphasizing or Newton meters. You have to know that a joule is a Newton meter. This is newtons times meters. You really need to know both of those. Okay, so once again, it's not a trick question, unfortunately, even though it seems like it is. If a question goes blah, 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 what's the potential energy of just this object? It can't have any potential energy by itself. You have to include the Earth in the system. Okay, so continuing talking about energies here. So mechanical energy, this is energy related to motion. So kinetic and potential, yeah. If they talk about mechanical energy, what is the total mechanical energy of all of the system? This is the sum of all potential and kinetic energies in the system total. Now in a closed system, again, it remains constant. Closed means there is no way for the energy to be dissipated, i.e. there is, again, no outside forces to the system. Oh, I forgot to do this one. What happens then is that the potential energy converts to kinetic. So if I keep holding things I shouldn't drop. So if I define, a little bird here, if I define my system to be the bird and the Earth, yeah, currently my system has energy. What kind of energy does it currently have? Potential, because I am holding the bird at a height off of the ground. So this system has potential energy. Once I drop it, what did I convert that potential energy to? Kinetic. It converted into motion, yeah? The only way this guy was going to be able to move is if something else gave it energy, yeah? So the height gives it the potential to have kinetic energy. Again, motion doesn't come from just nowhere, right? The fact that this guy does drop, it has to get that energy from somewhere, and it gets it from the height. Now, this conversion can happen back and forth, so I can go potential, kinetic, back and forth, like in a pendulum. If you guys know what a pendulum is, when I swing something back and forth, yeah, that's a conversion from potential to kinetic. Roller coasters we're going to talk about very often, actually, because roller coasters are designed on the concept of conservation of energy. The only way they work is by conservation of energy, converting from potential to kinetic, so forth and so on. Or a spring. Again, I let a spring go, and as I pull it, I'm giving it the potential. I let it go, pew, and it converts to kinetic. So this means we have a conversion between a height and a velocity, or again, a speed. If you read a problem and you realize there is a height and they're asking about a speed, or a speed and they're asking about a height, you are thinking in terms of conservation of energy and in this case, the conversion of energy. So what we're going to talk about in this lesson is a concept called energy bar charts. It's just a way to visualize a conversion of energy. We're not going to do a lot of calculations. It's just talking about it qualitatively, which means just visually. It's not an actual mathematic calculation. So again, with energy bar charts, what this means is as my potential energy increases in a system, yeah, what happens is that kinetic is going to decrease because in order for a closed system, yeah, in order for it to be a closed system, if I'm increasing my potential, that increase has to come from somewhere, and it would come from a decrease in the kinetic. But if I'm decreasing my potential, that means that kinetic increases, right? As this little guy drops, the height decreases, and so that's potential energy decreasing. So as that decrease happens, though, the speed of it increases. So we have this give and take. Yeah, if I give a little bit of potential, that goes into the kinetic. Now, what this really means is that the total, again, this right here, we would call total mechanical energy. I can feel my throat hurting. Sorry, guys. Even just recording this video. Okay, there we go. So total mechanical energy. So this is kinetic energy initial plus potential energy initial. Occasionally, you will see PE for potential energy. Again, it's actually U usually, but in this case, we can say PE. So my total initial is going to equal my total final. Yeah, because again, my energy is just getting converted. It's not going away, staying in the system. So as long as it's a closed system, again, if there's nothing outside the system that can add or take away energy, what ends up being is that we're going to make bar charts. Yeah, that shows the kinetic versus the potential. The total of all of these heights should be constant because my total initial should equal my total final. So let's go ahead and keep going. Oh, sorry. On to this roller coaster question. So it says a roller coaster, again, we talked about, is built entirely on the premise of energy conservation. I start with a height and then it goes, right? In order for the roller coaster to go, that energy has to come from somewhere, and it comes from the height. You should know that taller roller coasters go faster, right? Comes from the height. So we're going to assume that friction is totally negligible, because if friction is not negligible, it can't be a closed system. That friction is going to zap energy and slow it down. So we are starting at point A. So we are calling this our initial point. You can call your initial point whatever you want. It's a choice, right? Our math just has to follow. So this is our initial point. So what that means is any energy I have at that point, that's all the energy I get to use. It can be converted back and forth, but I cannot end up with more energy than I have to start with, or less in this case because friction is negligible. Again, if friction were not negligible, you would end up with less energy because friction is going to zap some of it. So we're going to make energy bar charts for each point. So what you do is you're going to label the types of energies we have. We have a height here. Yeah, this is a height. Let's go ahead and call our height. Again, this is my choice. I'm going to go ahead and just say to B, not all the way to the ground. So since B and D are the lowest points, we will call that our 0. You can choose, this is a choice. I'm choosing to call my lowest point 0, even though we are above the ground. So we're going to have 2 bar charts here. So again, what is the initial type of energy? If I'm at a height, what energy is based on a height? Potential energy, right? So I'm going to say UG. Now, they are just waiting. They come up to the top and they are just waiting to go, but they're at rest for that split second. Yeah. So if we're at rest, can there be any kinetic energy? No. So what this means is all of my energy is in potential. Yeah, there's no kinetic right there at the top. We're saying that it starts at rest. There can't be any kinetic energy if there's no motion. It's all in potential. Now, what I'm going to do here, just to you don't have to do this because again, this is really just a visual representation of how energy bar charts work. But I'm going to go ahead and divvy this up into. Let's go ahead and divvy it up into 6. So let's go half. That's 6. 1, 2, 3, 4, 5, 6. So let's go ahead and say that I have 6 potential energy. Again, this is just to understand how the conversion works. It's not actually 6. I'm just making up a number. The height of that energy bar chart is 6. So let's look at B. Now again, I am calling B my lowest point. And I've got my energies here. Yeah, I still had my potential and my kinetic. So I'm at my lowest point. Yeah. What happens is, again, if I'm at my lowest point, that means we now have no potential energy. I've lost all of my height that I had. Yeah, no potential. But that energy has to go somewhere. It can't be destroyed. Where does that energy go? It goes into kinetic. So from point A to point B, all of my potential energy got transferred into kinetic. So this guy also has a height of 6 because, again, I'm not creating energy, I'm not destroying energy, it's just being converted from one type to the other. So let's go ahead and say now U, G versus K for point C. Well, for point C, if you notice, C is not as high as A, right? But C is high. There is a height here. So let's think about this then. For my potential energy, would it have a height of 6 like these guys do? No, because it's not as high as it was to start with when I was at 6. So maybe let's say, I'm just making up numbers here. This is just to understand. Let's go ahead and say that it's a height of 5. So I've got 1, 2, 3, 4, 5. It's a height of 5. Because again, when I was at A, I had 6 potential energy. But I'm at C, I'm a little bit lower. I don't have as much potential energy. But this is a closed system. If I now only have 5 potential energy, where did that other energy go? It's in kinetic. And so I had 6 possible units of energy to start with. I only have 5 in the potential right now. So how much do I have in kinetic? 1, right? That's because this is a closed system. My energy is being converted. It is not being destroyed, it is not being created. If I only had 6 to work with, I gotta have 6 total, yeah, at any point. So with that in mind, I want you to do the bar charts for D and E. Now again, E, you'll notice, is not as high as C, it's not as high as A. You can go ahead and decide however much energy you want to give E. Your answer for kinetic needs to fall in line with that. So go ahead and do the bar charts for D and E. Okay, so D, notice, is the same height as B. B and D have the same height, so they actually are going to have the same bar chart. At that point, all of my energy is in kinetic. So 6. You should have a height of 6. Yes, height of 6. All of my energy is in kinetic. Now again, at point E though, I'm even lower than I was at point C. So I'm going to go ahead and say E looks about halfway, maybe a little bit less. So I'm going to say that I have 3 in potential, which based on that choice, yeah, that means that I have 3 in kinetic. I've only got 6 total units of energy to work with. The total has to be the same. Now, if you chose your potential to be 4 at this point, just again, it's just a qualitative, just trying to understand how this works. I'm just making up numbers. If I chose my potential to be 4, how many would I have in kinetic? 2, because my total amount of energy stays the same. It is not destroyed, it is not created, it is converted from one type to the other. So using these energy bar charts, we're going to answer these last questions. At what point is the roller coaster going the fastest? So let's look at our bar charts. Well, fast, something that's going fast is speed, right? And what type of energy is based on speed? Kinetic. So at what point, A, B, C, D, or E, is it going the fastest? Where does it have the most kinetic energy? Point B, right? At point B, and D, B and D has to be going the fastest there because all of my potential I had from the height gets converted into kinetic at the bottom. That's where it's going the fastest. So what I want you to do is I want you to answer 2, 3, and 4, thinking about the heights of the different types of energy to answer these questions. Okay, so number 2, how does the velocity at point C compare to the velocity at point B? Well, here is B compared to C. Here was my kinetic energy at B and my kinetic energy at C. Where is it going faster? Well, it's going faster at B, right? C has to be going slower because some of my energy is in potential, into the height. I converted that speed that I had at B and it goes shoom, and it converts into the height. So it's going slower at C because, again, some of that kinetic energy I had down at the bottom got converted into a height. And so I have to be slowing down. I have to be losing kinetic energy. Now it says, how does the potential energy at point A compare to the kinetic energy at point B? Well, at point A, all of my energy was in potential. At point B, all of my energy was in kinetic. So they are equal because that complete conversion happened. All of my height whoosh, got converted into a speed. Now it says number 4, if the hill at point E were taller than point A, so let's say that this hill goes all the way up here. Here's point E. Do you think the roller coaster would be able to reach that point? Why or why not? Well, by the law of conservation of energy, we only had 6 units of energy to start with. If I have a greater height, it will only go up as high as it started with because it's going to go up to that point. All of its energy will be converted back into potential and it's not going to have any more kinetic energy to keep going. So nope. All energy is converted. I'm going to do this. Is converted back to potential at the height of point A meaning it has no more speed left. So it will not have any more speed to reach point E. If point E was taken up higher than point A. Whew, okay, so again, even though this is introductory stuff and not calculations for the most part, there's those 2 formulas for kinetic and potential. You guys are going to be practicing in the homework. I know this is still kind of a long video. I hope it's making sense. On Monday, I'm going to do some practice problems with you guys to make sure that we have a good foundation in the basics of this before we get into the big calculation.